Hello, sir. Please unmute and let's start.
Yes, sir. I am just trying to find out that thermodynamics. Okay, got it. Got it. Hello, everyone. So I hope I am audible to each and every one of you. Could you please confirm if I am audible? So today, uh, okay, am I audible? So today we are going to continue our discussion on ICRB previous year questions. Okay, thank you. Thank you. Okay, so we are going to continue our discussion on ICRB previous year questions. And in this particular session, we are going to cover thermodynamics and its applications, ISRO previous year questions from the year 2020. Okay, so today's focus will be on 2020 ISRO paper, and we will be covering each and everything from basic to applied thermodynamics. Okay, so let us start the session. Let us start a session. But before that, let me give you a brief introduction about myself. So my name is Vipin Kumar Yadav, and I have done MTech from IIT Kharagpur. I've also done MS or MSc, whatever you want to call it, from Politecnico di Milano in Italy. And I have almost, in fact, more than 5 years of teaching experience for GATE, JEE, AE, ESC, and PSUs. Okay. So this is my very brief introduction for you. Okay. Of course, there is more to it. So let us start today's session with the very first question from the year 2020 in ISRO. Okay. So, okay, we will be covering around 12, 13 questions in this session. Okay. So, this is the first question for you. In the PV diagram, pressure volume diagram of a steady flow compressor, the intercooling can be represented as. So I hope that you have seen the diagram. I mean, when do you use intercooling? You use intercooling between two compression stills, right? So if you have one compressor, for example, something like this. If you have, this is one compressor, compression one, and fluid enters here at P1 and exits here at, let us say, an intermediate pressure Pi. Now the temperature and pressure both increases. For example, temperature here is T1, here temperature is Ti. Okay, so Ti is greater than T1 and Pi is greater than P1. Now you want to compress it again, but the temperature is really high. Okay, so you cannot just send it to the another compressor. What do? You use intercooling in between. Before you do second compression, you use intercooling. So intercooler, and this intercooler reduces the temperature back to T1. You see, From Ti, the temperature is reduced back to T1, but at constant pressure. So pressure will remain same, Pi. And then you will send it to another compressor for further compression. Okay, so let us say this is P2 and T2. So intercooler is used between two compressors and for constant pressure. So intercooler, it is basically constant pressure cooling, constant pressure cooling. Now, how do we draw this in a PV diagram? How do we draw this in a PV diagram? So let us say this is your pressure volume diagram. Okay. So you see how many pressures are there? You have P1, Pi, and P2. So basically you have three different pressures. Let us say this is your P1, this is your intermediate pressure Pi, and this is your P2. Okay. So you are working between three pressures. Now, first of all, what will happen? Compression will happen in the compression one. How? Isentropic compression. So from one, you will go to intermediate pressure I. Now you do constant pressure cooling. Constant pressure means what? A horizontal line, and the temperature will reduce to Ti. Okay, so this is your intermediate pressure itself. And then you increase the pressure one more time to the point 2. So this is your compression with inter. So this stage is called as intercooling. This stage is called as intercooling. Okay. And how can you show this in a PV diagram? With a horizontal line. So how do you show it? With a horizontal line. Okay. So what is the right answer? In the PV diagram, the intercooling can be represented as horizontal line. Horizontal line. Okay. So this is your right answer. Got it? Let's go to the next question. Okay, very simple question. Very, very simple question. A hot body at, so we have a hot body and let us say its temperature is 1000 Kelvin and it is transferring 2000 kilojoule of heat to a body at 500 Kelvin. So it is transferring means rejecting Q is equals to 2000 kilojoule to the body at temperature, lower temperature 500 Kelvin. Determine the net entropy change. Net means total entropy change. So what is total or net entropy change? Is basically entropy change in the first system and entropy change in the second system. This one. Okay. So one is system, the other is surrounding. Okay. So now you see, you have to know what formula we can apply here. So this, you see, it is a reservoir. It is a reservoir. Its temperature is constant. So this is isothermal heat transfer. So for this, it is isothermal heat rejection. And for this body, it is isothermal heat absorption. Okay. So now you should know how to calculate entropy when the temperature remains constant. So it is Q by T1. But Q what? Negative because heat rejected. Plus Q by T2. So this will be positive, right? Because heat is absorbed. So it is equals to minus 2000 by 1000 plus 2000 by 500. So minus 2 plus 4 is equals to plus 2 kilojoule per kg. Kilojoule per kg. So the total entropy change or the net entropy change of both the systems or both the bodies is plus 2 kilojoule per kg. Plus 2 kilojoule per kg. Okay. I hope it is clear. Yes. Chalo. Let's move on to the highest ratio of specific heat is possible for argon, helium, hydrogen, or air. Okay. So it here helium is a monoatomic gas. Even argon is a monoatomic gas. Hydrogen is H2. Okay, and air is also diatomic. So basically, here you have to understand one thing that gamma, the relationship between gamma and degree of freedom F is given as gamma is equals to F plus 2 by F. Here gamma is what? Ratio of specific heats and F is degree of freedom. And degree of freedom, how do you get? Degree of freedom is basically F is equals to 3n minus K. Okay. Now for monoatomic gases, N is equals to 1. So F is equals to, and K is equals to here 0. Okay. So F is equals to 3. When I talk about diatomic, here N is equals to 2 and F is equals to 5. Okay. Triatomic, N is equals to 3 and F is equals to 6. So here for diatomic, for example, air or hydrogen, your gamma is equals to 5 plus 2 by 5 is equals to 7 by 5 or 1.4. So for air or hydrogen, you have this. For helium, what is F? 3 plus 2 by 3. So 5 by 3, it is 1.67. Okay. So helium has a higher ratio of specific heats compared to other gases. Okay. So helium is the correct answer. Let's move on. Which of the following can be used to determine the variation of saturation, pressure, and temperature along phase boundaries? Or this is very simple. This is very simple. What do you have? So you have these four equations, relations, and they are asking which relates saturation, temperature, and pressure along phase boundary. So what about Joule's Thomson relation? Now, if you know, we do this in the throttling process. So it gives you a relationship between temperature and pressure, general temperature and pressure, at constant enthalpy. So mu J, which is Joule's Thomson coefficient, is equals to dt by change in temperature by change in pressure at constant enthalpy. Okay. What about Carnot equation? Carnot equation, we all know, basically Carnot equation gives you heat transfer and it is equals to temperature into change of flow of entropy. Okay, or flow entropy. This is your Carnot equation. So this is also not correct. What about Rankine H Houernot's relation? So this basically gives you conservation equations. Conservation equations of mass, momentum, and energy across the shock wave. Across the shock wave. So this is also not our answer. Finally, D. Now I guess you already know what is the right answer. Now Clausius-Clapeyron gives you variation of saturation temperature and pressure along phase boundaries. Phase boundaries. So how do you give the equation? Change of pressure by change of temperature at constant volume is equals to ds by dv at constant temperature. Okay, so this is your Clausius-Clapeyron equation. So right answer is Clausius-Clapeyron equation. Clausius-Clapeyron equation. Okay, got it? Chalo. Let's move on to the next question. Now air at 27 degrees Celsius and 100 kilopascal enters in a steady nozzle. So what do you have? A nozzle. At the velocity v1 is equals to 100 meter per second. If the inlet area, yeah, that is A1 is equals to 0.5 meter square, what is the mass flow rate? So you see, mass flow rate is mass conservation. So M1 is equals to M2. Here also it will be same. If M1 is here, M2 is there, it's same. Okay. Now, and this is equals to rho AV, mass flow rate, rho AV, area into velocity, density, area into velocity. So if I talk about m dot 1 is equals to rho 1, area 1, V1. Okay. Now I know A1 and V1. You see, A1 and V1. A1 is 0.5, V1 is 100. What about rho 1? Rho 1 I need to calculate. How do I calculate? By it is air, that means I can apply ideal gas equation. PV is equals to mRT. So P is equals to M by V RT, or density into RT. So density here is P1. Density 1 is equals to P1 upon R T1. Now pressure is given 100 kilopascal. R is 0.287 and temperature is 27 degrees Celsius. That means 300. So density 1 is equals to 1.16 kg per meter square. So now I can substitute 1.16 into 0.5 into 100. So it is 58 kg per second. 58 kg per second is your right answer. Okay. So 58 kg per second is your right answer. So I hope it is clear. Yes. So let's move on to the next question. Critical point of water is. So this is a very general question. You must remember this. So critical point of water is basically critical pressure is given as 220.6 bar or 22.06 megapascal. What is the temperature, critical temperature? 373.95 degrees Celsius. And specific volume is 0.005155 meter cube per kg. So there are the conditions that this basically gives you, and it is fixed. Okay, so at critical point, degree of freedom is also 0. Okay, so this point is fixed. Critical pressure, critical temperature, critical volume. So what is the right answer? B is the right answer. Critical pressure is this. Okay. This is straightforward question. It should not take less than 5 seconds to solve this. I mean, to give the right answer. Okay. There is nothing to solve here. It is a straightforward question. Okay. Chalo. How about this question? In a shower mixture, cold water. So basically, let us say you have a mixture. Hot water is coming in, cold water is coming in. And so cold water is coming at mass flow rate is 5 kg per minute and temperature is equals 27 degrees Celsius means 300 Kelvin. And it is mixed with hot water. Hot water mass flow rate of hot water is 15 kg per minute and temperature of 1 TC1 is 77. So 77 is how much? 350 Kelvin. And here they are going to mix together. You see, here they are going to mix together. So, and eventually they will reach to a final temperature, Okay. So you need to find out the final temperature. Now there are two ways of doing it. You can do energy balance. Energy balance E in is equals to E out. Okay. So you can do mass, or you can do like this. Energy of cold fluid plus energy of hot fluid is equals to energy of mixture. That is how you can do it. Or there is another way of doing it. What? By when they will mix, when hot and cold fluid will mix here, Q rejected by hot fluid is equals to Q absorbed, or energy, you can also say energy absorbed by cold fluid. So this is how we are going to do it. Okay, so let me take this on the other page. So what can I say? Heat rejected by hot fluid is equals to heat absorbed by cold fluid. Now how much heat is rejected? M hot Cp hot into T initial minus T final. Okay. And how much heat is? So basically it should be T final minus T initial. Okay, but it is rejecting, so I have to put minus here. So eventually I can write CPH. These things are very obvious, so I hope you should know this. Okay. Now what about cold? Cold is, it is absorbing anyway, so CPC T final minus T initial. Okay. Now I can, it is water both, so I can cancel this. Hot one is 15 kg per minute. T initial is 350 minus TF. M dot C is how much? 5 kg per minute. T final I need to find out minus T initial. So T initial is how much? It is 300. Okay. So I can also write how much? 350 minus TF into 3 is equals to TF minus 300. Okay. So it is 1050 minus 3TF is equals to TF minus 300. So if I solve this, I will get TF is equals to 337.5 Kelvin or 64.5 degree Celsius. 64.5 degree Celsius. Okay. So this is your right answer. 64.5 degrees Celsius. B is the right answer. Okay. So I hope this is clear. 64.5. Okay. Now, next question. Which of the following uses a regenerator? So this is very simple. Okay, Breton cycle is basically gas cycle. Okay, we do not use regenerator here. It is a gas cycle. So we do not use regenerator here. What is a regenerator? Regenerator is basically a device. It is a storage device basically. Okay, so there are matrices here, which is very high thermal conductivity. So once what will happen? Of hot fluid will flow in. Hot fluid will flow in, and these matrices will store heat. It will store heat, and when this it flows like this. So this is hot fluid. Then what will happen? A cold fluid will flow in. Cold fluid will flow in. It will absorb heat from the matrices and go out. Okay. So it is called as regenerator. It is a regenerator. Okay. Same thing, same device is working as hot heat exchanger and cold heat exchanger. And it is used in Stirling and addiction cycle. So Stirling cycle is what? We use our two isothermal processes and two, which process? Isochoric processes. Erection is what? Two isothermal, of course. So you just 1 second. So isothermal processes and two isobaric constant pressure processes. So basically, you see these have isothermal processes. And therefore, these two cycles are derived from Carnot cycle. Okay, their efficiencies are very close to Carnot cycle. Okay, but again, isothermal process is impossible to achieve. So to get as close to as isothermal process, we use a regenerator. We use a regenerator in Erikson and Stirling cycle. Okay, the right answer is both B and C. Both B and C. Okay. So I hope this is clear. Okay, let's move on. So a gas is contained in a cylinder. Let me take it on another page. So basically what we have a cylinder with a movable piston. So piston can move, okay? And it contains mass of 100 kg of gas. Now heat is flowing in, Q in is equals to 2500 joule. And because of this, the internal energy of the gas, so delta U is equals to 1500. Okay. What is the distance? So because of this heat transfer, what will happen? Some work transfer will also be there. Okay. Because the piston will move. Okay. You are transferring heat, so piston will move. So piston will move from this location to a certain location here, let us say. And this is, let us say, X. So this heat transfer will basically lead to a pressure or a force on this piston. Okay. So how can I write this? I can write first law of thermodynamics is given by Qn is equals to delta U plus work output. So what is Qn? By they have given in question 2500. What is delta U? 1500 plus work output. So work output is equals to 1000 joules. Now this is work output. Now how are you getting this work output? By pushing this piston outward, by pushing this piston outward. So this work output is equals to force into displacement x. Force into displacement x. So this is what 1000. Force is what m g into x. Now I need to find the distance or displacement. It is m is how much? 100 kg into 9.81. So this is basically almost 1 meter, almost 1 meter. Okay. So 1 meter is the correct answer. B is the correct answer. Okay. Because you see, this will cut and this is 10, this is 9.81. So it is almost 1 meter, almost 1 meter. Got it? So let's move ahead. The next question. Okay. Let's move ahead to the next question. What is the next question? Okay. A refrigerator with a COP of 5 is used in a room at 300 Kelvin. At 300 Kelvin. What will be the heat intake through a section of refrigerator wall of area 100 centimeter into 100 centimeter with a thickness of 10 centimeter, assuming only conduction? Value of thermal conductivity of the wall can be this. Okay. So basically, we have a refrigerator with COP of 5 is used in a room at 300 Kelvin. What will be the heat intake? Okay. So basically, you see what they are trying to say is they are trying to tell you that you have a room. You see, you have, this is your room, and the temperature inside the room, T of room, is equals to 300 Kelvin. Okay. Now this is your refrigerator. This is your refrigerator here. Now inside the refrigerator, you are maintaining a temperature whatever, let us say TL. And they are saying that this wall of this refrigerator so the area of wall is given and the thickness is also given. So this, let us say this thickness is 10 centimeter. So because of this room is at higher temperature, heat will flow in. Okay, Q in. This is what I need to find out. What do we need to find out? What will be the heat intake? Yes, Q in I need to find out. Now, how do I find out Q in? So Q in is equals to minus K area by conduction. Okay, only by conduction. dt by dx. So you see the K is given. K is how much conductivity? 1 watt per centimeter cube. So if K is equals to 1 watt per centimeter Kelvin, if I convert this into meter, so it is 100 watt per meter Kelvin. So it is minus 100. Area is how much? Area is 100 centimeter into 100 centimeter. So it is basically 1. Okay. Into 1 into 1 meter. 1 meter square. Okay. Now dt is T lower minus T higher, which is room temperature, upon distance, upon thickness is how much? 0.1. Okay, so this higher is basically room temperature. This higher is room temperature. I need to find out T lower. I need to find out T lower. Okay, so what is T lower? Now, as this is the refrigerator, okay, the purpose of refrigerator is to throw out this Q in. Whatever Q in is coming, it has to throw out. Okay, so COP of this refrigerator, if I want to draw, I can draw it like this. So this is my T higher, which is 300 Kelvin. This is my refrigerator, and this is lower temperature that I need to find out. Now Q I need to throw out. Okay, this Q I need to Q2, and this is Q1, and this is work input. Okay, the refrigerator with COP of 5 is used. Okay, so basically I don't see anywhere that they have written it is a reversible refrigerator, but I have no choice but to use temperature because I need to find out temperature. Okay, I need to find out temperatures. So I will use COP of this refrigerator is equals to T lower upon T higher minus T lower. Okay, so it will give you the lowest temperature. It will give you the lowest temperature. Okay, 5 is equals to TL upon 300 minus TL. So TL, if you calculate, it is 250 Kelvin. 250 Kelvin. Okay, now I am sorted. 100 into 1, 250 minus 300 upon 0.1. So Q in is equals to 50,000 watts. 50,000 watts. Okay, so this is your answer. 50,000. 1 second. Is it 50,000? So this is 50, 100 into 50. So I think there is some misprint in the answers. It should be 50,000. Instead of this, it is 50,000. Okay. So A is the correct answer. I think there is some misprint here. Okay. Chalo, anyway. Anyway, I think it is 50,000 itself. Okay. Got it? Let's move on to the next question. Okay. Now, a mass of 1 kg of air. Okay, we have a diesel cycle here. So let me take this on another page. What do we have? We have a diesel cycle. So I hope you all know diesel cycle, right? PV. Okay. One constant pressure process. One constant pressure process. One constant volume process. One, two, three, four. This is constant pressure, heat addition. This is isentropic expansion. So these both are isentropic process. Okay, isentropic compression and expansion. This is constant volume. So you see, 1 to 2 is isentropic compression. And 3 to 4 is isentropic expansion. Now what the question is saying? Mass of air is equals to 1 kg and temperature is equals to 300 Kelvin and pressure is equals to 0.98 atmosphere is taken through the diesel cycle. Compression ratio is R is given. What is R? V1 by V2. Volume before compression and divided by after compression is equals to 16. Calculate the temperature of the air after compression. So T2 I need to calculate. T1 is given. T2 I need to calculate and take gamma is equals to 1.5. Gamma is equals to 1.5. So it's very simple. You see, I know that 1 to 2 is isentropic compression. So for 1 to 2, can I write T2 by T1 is equals to P2 by P1, gamma minus 1 by gamma, and V1 by V2, gamma minus 1. Simple. So I need to find out T2. And I already know this. So T2 by T1. What is V1 by V2? R, compression ratio, gamma minus 1. Now R is 16. Gamma is 1.5 they have given in question. So this. So T2 is equals to T1 is what? 300 into 16, 0.5. So if you solve this, you will have 1200 Kelvin. 1200 Kelvin. Okay. So now a lot of people will directly mark the answer A, but you have to understand this units are in degrees Celsius. So I need to convert it into degrees Celsius, which is 927 degrees Celsius. Okay. So if you go and mark A, you will just lose your marks. Okay. 927 degrees Celsius is the correct answer. Is the correct answer. Okay. So I hope this is clear. I hope this is clear. Okay. Got it? Chalo. So I think this was the last question for this session. Okay. In a two-component system, this is also one question. In a two-component system, if the non-compositional variation is only temperature, the number of degree of freedom, in the case of a single phase field as per Gibbs phase rule is. So what is Gibbs phase rule? Gibbs phase rule gives you degree of freedom. Gibbs phase rule is equals to P plus F is equals to C plus 2. What is this? Number of phases. This is basically degree of freedom, and that is component number of component. Okay. So they are saying two component system. That means C is equals to 2. And they are saying single phase field, that means phase is equals to 1. So I can say 1 plus F is equals to 2 plus 2. F is equals to 4 minus 1. So degree of freedom for this particular component is 3. Okay. They are saying two component system and single phase field. Okay. So phase is 1. So D is the correct answer. D is the correct answer. Okay. So yeah, this was the last question, I think. Yes. Okay. So this was the previous year questions from thermodynamics and its applications in the ISRO 2020. Now again you see most of the question are conceptual based. Now if you do not know the concepts, if you have just remembered the formulas and you're trying to put the values in this, it is not going to work out. Concepts are really important. Concepts are really important. Okay, so keep revising, keep learning the understanding the concept basically. Okay, that will actually be helpful for you. Okay, so we are going to stop here. Okay, and I will see you in the next further classes. Okay, thank you so much.